Welcome to Week 7 of the Introduction 2020 Faculty Perspective Series. Today's roundup of faculty talks will feature faculty from the School of Journalism and Communication, the Department of Indigenous Race and Ethnic Studies, the Department of Earth Sciences, the Department of Biology, and Cinema Studies. In a moment, I will turn the program over to our presenter, Dr. Thomas Giachetti. Before that, though, I'm going to review a few things that are important to keeping you on track to complete your introduction requirements. All students watching this program should make time to submit your reflection of this session as soon as we're done. You can do that at community.uoregon.edu. Your reflections on the individual faculty perspectives programs don't have to be long, but we do want you to share what you've learned. Generally speaking, taking time to reflect in this way is a proven way to improve your retention of material and is a habit of tons of successful students. If you're a student who wants to earn a credit as part of introduction, you need to select all the faculty perspectives within 2 full tracks, plus 4 additional talks, and submit reflections on all 20. You'll also need to submit a longer capstone reflection on the entirety of the programs and what you've learned. Finally, for those students who are watching live, remember that our faculty members answer your questions at the end of at the last segment, and they do that live on camera during each one of these programs. If you're a student watching live in Zoom, please use the Q&A feature at the bottom of your Zoom screen to ask our faculty presenter your questions. So at this time, I'm really excited to be able to introduce you to our faculty presenter for this session. In this week's Environment and Climate Change track, Dr. Thomas Giachetti explores what can be learned about an explosive volcanic eruption from the deposits it leaves behind. Welcome, Dr. Giachetti.
Thank you, Cora. Good afternoon, everybody. So my name is Thomas Giachetti, as Cora just said. I'm an assistant professor in volcanology in the Department of Earth Sciences here at the University of Oregon. And today, since we cannot really do that as we would do in normal times, I will try to have you go outside and see things in the wild and what we can learn about volcanoes from the deposit they leave behind. So a little bit about me. One of the first things you can probably notice is that English is not my mother tongue. I'm a French volcanologist. I was born, raised, and actually educated in France. I got my PhD in France. And I moved to the US about 9 years ago actually, for work. I got a postdoc in Houston, Texas, and then I moved to Ann Arbor, Michigan, and I moved to the University of Oregon to start this position of assistant professor only 5 years ago. One thing you need to know about me is that I'm doing this job really by passion. All these pictures that you can see right now on the screen, I've had the chance to take them either during my studies, during my PhD, or during my work here at the University of Oregon, or even during vacation, like those pictures from Hawaii or Stromboli in Italy. Why did I decide one day to become a volcanologist? Well, that's because thanks to, I should say, these guys, Maurice and Katja Kraft, that you can see here in the middle of the screen, who were French volcanologists who tragically died in 1991 during an eruption. And I was 12, I was sick, maybe the flu, in the middle of winter, and I turn on TV and I see a documentary about their life with all the pictures that you can see around them here on the screen. They took these pictures. And I quickly become amazed by how powerful can be volcanoes, and even without knowing anything about geology, you can see red, you can see gray, you can see lava flow, you can see very big explosion. You can see names from all over the world, the US, Indonesia, Tanzania here on the screen, or Iceland. And so I decided when I was 12 to try to be a volcanologist. And so moving from the north of France, where there's absolutely no volcano, to the central part of France where there are so many nice volcanoes called the Chaîne des Puys, where I did all my studies and my PhD, to the US to find a postdoc and, as I told you, a position here at the University of Oregon. And I will show you in a moment why it makes so much sense to have volcanologists here at the University of Oregon. So when I saw these pictures and starting my studies, I quickly realized that not only volcanoes are nice and beautiful and there's always sound and vision and even smell associated to them, they are also very dangerous. More than 5 million persons were affected by volcanoes in the 20th century. More than 90,000 of them were killed. And as you may remember from your, I don't know, high school classes, the Earth is divided, the surface of the Earth is divided in several large tectonic plates. And so wherever you've got boundaries between tectonic plates, you've got volcanism. So that's what you can see on the map here, where you see triangles for all the volcanoes that erupted either during the last century or sometime in the last 10,000 years. And as you can see, they are not completely randomly distributed on the surface of the Earth, but follow boundaries in between plates. And you can see that most of them are actually located on subduction zones. So that's when one plate is going beneath the other one, and that's where volcanoes are usually the most dangerous. You can see some pictures of at the bottom of some of the surface processes that these volcanoes, subduction zone volcanoes, can produce. On the right, you've got Lars from Mount St. Helens, which is just a 3-hour drive from Eugene. And on the left, you've got ashfall from Mount Pinatubo, and in the middle, pyroclastic flow, pyroclastic surge from the same eruption of Mount Pinatubo in Philippines in 1991. So if you look at the map again, you see a very thick black line that is crossing the Pacific plate. And so if we look at the cross section of the Pacific plate, more or less you can see the different types of volcanoes and different types of volcanism that you can get at the surface of the Earth. So if we look at this big picture, starting from the left, you've got a subduction zone between two oceanic plates. So that would be places like Japan or New Zealand, for example. On the extreme right, you've got a continental rift. So that would be, for example, volcanoes like Newberry volcano. Some of you maybe don't know Newberry. We'll see that in a moment. And in between, you've got continental subduction zone. So like our Cascades volcanoes here in the Pacific Northwest. You've got the mid-oceanic ridge. That's where the oceanic crust is being produced everywhere on Earth. That's actually where more than 75% of the magma produced on Earth is produced beneath kilometers of water, so a volcanism that we have a hard time to witness because it's really difficult to go there. And in between, the shield volcano, so that's a type of volcano that is built through an hotspot, so that would be Hawaii, of course. And so, as I said before, subduction zone volcanoes are usually the most powerful and the most dangerous. So why do we study volcanoes? Of course, to understand why they can be so dangerous and how to protect population from these volcanoes. And why do we do it here in Oregon? Well, if you look at this map where you see Eugene here in the middle with this green dot, and you just trace a circle of 1,000 kilometer radius, you can see that we've got almost all types of volcanism. So starting to the top left with subduction zone volcanoes like Mount St. Helens. So that's a picture from its eruption in 1980. On the top right, we've got an hotspot, but not through a continental crust this time, but through not through oceanic crust, but through a continental crust this time. That's the Yellowstone, which is also a national park. On the bottom right, we've got Newberry volcano, which is, again, about 3 hours drive from Eugene. I really encourage you to go there if you can, now or later when you come to Oregon. That's really such a nice place beyond like its richness in volcanic features. And on the bottom left, you can see the Juan de Fuca mid-oceanic ridge. So that's a picture that was taken several hundred meters beneath the sea surface that shows here what we usually call a black smoker. So that's hydrothermal fluid being released at the bottom of the ocean and making this very dark gray smoke-like feature. So actually, if we look at Eugene and the Cascades, the United States Geological Survey, or USGS, who is in charge of monitoring our volcanoes here in the US, has classified 12 volcanoes as having a high to very high threat potential. 7 of these volcanoes in the Cascades that you can see here with the white dots on the map on the left. 7 of these volcanoes have erupted over the last 250 years. And the last major eruption is only 40 years old, actually this year, and it's the eruption of Mount St. Helens, or Lower Clough, as it's called by the native here. But the big eruption, the last very, very big eruption in the Pacific Northwest is that of Mount Mazama. that created Crater Lake about 8,000 years ago. So you can see a nice aerial picture of Crater Lake on the top left, and a nice picture of the caldera during the winter at the bottom. And what you see on the top right is what happened during this eruption. So we had a big volcano with a big magma chamber beneath, and during the eruption, it did not start at the center of the volcano, but rather on the side, and triggered eruption all around the summit, and that led to empty the magma chamber, therefore leaving a big void in the crust, and so that couldn't hold the roof of the magma chamber anymore, and the roof collapsed, and like a piston more or less, and so that made a big hole that was then filled with water, and that is creating Crater Lake, which is actually the deepest natural lake in the continental US. So why do we study volcanoes here? I just show you that. How do we do that? Here at the University of Oregon, we've got the chance to have a center for volcanology, meaning we've got 11 faculties whose research is principally or partly focused on volcanoes and their activity. And so that can go from how do you create magma in the crust or in the mantle, how does this magma is transported through the crust, to how it erupts at the surface and the consequence of its eruptions. On top of having 11 faculties, we've got every year more than 20 master and PhD students, and we've got also postdoc and research scientists. And something that is probably more interesting for you, we've got also a lot of undergrads working with us in our labs every single year. So right now it's a bit tricky, of course, with all the situation to have people working in our lab, but in normal year I always have 2 or 3 person playing with rocks in my lab or images and so on. So you should definitely ask me and my colleagues about a potential opportunity to work in our lab. So in my group in particular that you can see on the right, so it's me and 3 PhD students, Josh, Caddy, and Monse. You can see first that the atmosphere in our group is pretty fun. So on top of doing working hard and trying to produce good science, we also have fun. Remember, I do this job by passion, so I really want my students also to have fun when they come to the lab and they want to just come and work. And we try to answer some very simple question in a way. For example, why and how does a volcanic eruption start and stop? What controls the explosiveness of an eruption, whether it will be effusive or explosive? What causes shifts from one activity to another? And can we anticipate the continuity of an eruption, meaning over the few hours to days to sometimes months of an eruption, can we predict how it will evolve? So altogether, we work on a bunch of volcanoes, most of them in the Cascades, because it's really easy to go there. It's, as I said, few-hour drives from Eugene. You can bring back almost as many samples as you want in a big truck. It's more tricky when you study a volcano that is far away and you need to select which sample you take to go back in the plane. So we work on Medicine Lake volcano in California, and Newberry volcano and Crater Lake here in Oregon, and Monse with Costa Rican actually is working on Poas and Toyalba volcano in Costa Rica. So how do we approach this question? In general, there are many ways to approach volcanoes. Remember, we can record and analyze only things we see at the surface. So most of the processes associated with volcanic eruption are hidden just because they occur in the crust. So you can either use the deposit they leave behind, so what I do, so go in the field, map and describe deposits of past eruption, collect samples, and then go back in the lab to analyze these samples collected in the field. You can monitor these active volcanoes or even those that are not active or not active at the moment. So that mainly is the role of the USGS. Or you can try to reproduce processes that you cannot see and that happen in the crust. So you can in the lab, and we've got some colleagues here who do that at the University of Oregon. They have instruments that are able to reproduce the condition of temperature, pressure, composition, and so on that occur in the crust to study what should happen based on what we know. Another way to also study volcano that is sometimes a standalone approach or can be complementary to the other approaches is numerical modeling or theoretical approach. And so that's what you can see on the bottom right of the screen. Here is an example of a numerical simulation of what would happen if part of a volcano would collapse in the sea and what kind of waves it would produce. And so that was a study that we've done in 2012, and actually this volcano collapsed in 2018 and killed more than 400 people in Indonesia. So all of these approaches, whichever they are, they involve a lot of a lot of instrument. They involve physics, math, chemistry, engineering. You can also, of course, be interested in the social and cultural aspect of volcanoes, and that's another area of volcano that can be studied. So I decided to focus a little bit more the talk now on what we can learn from an explosive eruption from the deposit it leaves behind. So most of the past almost 9 years, actually, I've been working at Medicine Lake Volcano in California. So you can see here on the map on the left that it's about 4 hours drive from Eugene to the south. It's a very nice place, very wild. It's not a national nor state park, so it's pretty remote. It's hard actually to find places to stay around if you don't want to camp, for example. And I've been focusing my work on the last eruption of Medicine Lake Volcano that is about 1,000 years old. And this eruption started explosively and released a lot of pumices. And you can see at the bottom this panoramic view of a quarry that is currently exploiting these pumices to make light cement, for example, or light stones. And the second part of the eruption was effusive, and it led to the emplacement of lava flows, obsidian flows that you can see here from the aerial view on the right of the image. So, having a volcano producing both explosive and effusive activity is very common with subduction volcanoes. So you can see here 2 pictures. On the left is Mount St. Helens in 1980. So some of your parents or grandparents, if you live in the Pacific Northwest, probably remember this famous eruption. And on the right is also Mount St. Helens about 25 years later. And many of you may know that Mount St. Helens erupted in 1980 without knowing that it actually also erupted between 2004 and 2008. But this eruption was effusive, and so of course less impressive, less dangerous, and therefore less known. So that shows you that a single volcano can produce very different types of activities, and you better know which one you would have in order to better assess hazards and mitigate risk. So Medicine Lake Volcano, the last eruption was similar, except that we had the 2 phases during the same eruption. On the left, you see again this quarry with all the pumices, so very explosive. And on the right, you see a closer view of the obsidian. So if we take even a closer view of these 2 products, you see pumices on the left here and obsidian on the right. And to see it even better, I brought some samples here that you can see. So this is a pumice from Medicine Lake Volcano, and this is an obsidian. And it might be very surprising, but these 2 rocks were actually the exact same magma to begin with. Meaning it's the same chemical composition, it's the same amount of crystal, except, and you can see very clearly with the camera, this one is whitish, this one is blackish, this one is full, the pumice is full of tiny voids, tiny vesicles, as we call them, while this one is pretty dense and glassy. And actually, this one is full of void. It's actually about 75-80% of void. And if you place it in a bowl with water, it actually floats. And remember, these are 2 products of the same volcano during the same eruption, except 2 phases. So how can we actually explain these differences? Well, if you see on the cross-section of a conduit that is here on the screen in the center, you start with the same magma at the bottom. This magma is full of volatiles, and so you know volatiles, you know carbon dioxide, for example, in your soda. So this is a volatile that is actually dissolved. If you take, when you buy your bottle of soda, you don't see any bubble yet. right? And it's because the gas is dissolved. It's the same for the magma, except that most of the volatile in the magma is water. What happens when the magma is rising towards the surface? The pressure is decreasing. And how could you mimic that with your bottle? Well, decreasing the pressure would be removing the lid of your bottle. For example, if you squeeze the bottle when it's closed, it's really hard. If you open it, it's more soft. It's because you release pressure. So if I give you a bottle of soda, the same bottle of soda, and I shake it and I ask you, can you open it without putting soda everywhere, or can you open it putting soda everywhere? What would you do? Probably in the first case, the explosive case, you would quickly open the bottom, and that you would release the pressure very, very fast. And that would lead to a quick exsolution of the volatiles. So that's when the dissolved volatiles turn into tiny bubbles that then grow and that rise to the surface. And they do that so quickly in the bottle of soda that it's making an explosive eruption. While if you wanted to not pour soda everywhere, you would slowly open your bottle and you would hear for the shh of the pressure being released. And with the same initial magma, in your case soda, you could make two different types of eruption. That's exactly the same thing with the magma. In one case on the left, it's rising very, very quickly. And so you're producing explosive eruption, to simplify, and on the right you can erupt your magma, but in a more less explosive way. So to study these processes on the field, we first need sample. And so that's why we go in the field. Sometimes you go in a quarry, it's really nice and easy, but sometimes you actually have to dig. And so this is a time lapse of me and my colleague from University of Hawaii digging in the wild at Medicine Lake. And so you must have seen us digging and standing and looking at the deposit and discussing whether what we see, and in the end we collect some samples. Then we turn whatever we see on the field. So for example, the picture on the left is a section in the big quarry that I've shown you before, and you can see that we've made some kind of stairs to refresh a bit the outcrop and be able to see the different layers. And so from the picture on the left, which is about 14 meters of deposit, so 46 feet, we turned that into a description of the deposit in the middle, where you can see different layers based on the size of the class. So that's how we call every tiny rock. The size of the class, whether they are obsidian or pieces of obsidian or pieces of pumices, the proportion of pumices and obsidian, and so on. So then what we do, you can see all these little arrows on the strat column. That's how we call the picture in the middle. There's some little triangle. Each triangle is a sample, meaning we've taken so many samples throughout the explosive deposit, because as you can see from the description in the middle, there are layers. It's not all the same thing all the way from the bottom to the top. It changes with time, because remember, here we're looking at the deposit. So whatever was deposited first is the beginning of the eruption, and what was deposited last is the end of the eruption. So the idea is, if we can look at some properties of these rocks from the bottom to the top, we are looking at properties of this rock through time. And maybe we will have some indication that at some point towards the end of the explosive phase, this eruption will turn into something effusive. So just from the field, we've seen that the explosive phase is not steady, but rather like pulses. That was one of the main findings. By digging a lot of pits, actually, I think now we are at 150 pits dug over the last few years. Some of them are very tiny, maybe like, I don't know, 10 or 15 centimeters. Some of them are 14 meters, as you can see here, so that requires a lot of time. We've seen also that this explosive phase was not just one big plume, meaning a volcanic plume, but rather at least two main plumes. And so that's something nobody can tell us, because this eruption took place about 1,000 years ago, and except if you dig into the deposit, you won't be able to have any information about this eruption. So the picture on the right here shows you some of the sample collected, and then what we do, we go back to our lab. So in my lab, we've got, for example, the instrument that you can see on the top right. And this one is used to measure the size distribution of particles. So if you take a sample, so what I call a sample is just not one rock, but it's rather like a big Ziploc bag, like a gallon Ziploc bag worth of deposit. And you've got rocks that are pretty big, as the one I showed you before, that pumice that is now all soaked with water. And some of them are very tiny. You barely see them by eye. And the size distribution, meaning how much of the very fine particle versus the large particle you have, and how this size distribution is changing with time, is something very important that we want to know. That will help us to, for example, say how violent was the fragmentation mechanism. So the fragmentation is when the magma is rising in the conduit. And remember, it's one body of liquid with some bubbles in it. And that at fragmentation, it turns into particles, solid particles, which are the rocks that I just showed you, carried in a gas phase. And so the fragmentation mechanism, depending on whether how violent it is, it will change the size distribution of the samples. And so this instrument on the top right is just something very easy to understand. You've got your particles that are falling in front of a white background, and you've got a high-speed camera that is just detecting every single particle and turn this particle, you know, the black images that you see at the bottom, into a size. Then we may want to see in individual class, like, can we see bubbles? Can we see bubbles, like even tiny bubbles we cannot see by eyes? To do that, we go to some instrument that we have here on campus in CamCore. So it's an underground facility with a lot of high-tech instrument, including the two that you have on the left here. On the top left is called an electronic microprobe. So that tells us the chemical composition of the glass or the crystal in the rock. And the one on the bottom left is called a scanning electron microscope. So it's just a fancy microscope that allows you to see very tiny features in your sample. But the problem with these two instruments is that they are destructive, in the sense that you need to take your sample and cut a slice through it. And you might lose some information about the whole texture of the glass. And so that's why more and more in the earth sciences, we try to use non-destructive instrument that allows us to see the sample, the structure of the sample in 3 dimensions. And we use X-ray microtomograph or X-ray microscope. And actually, we just have such instrument, a very high-tech and expensive instrument that arrived at University of Oregon and that will be hosted in my campus. So that's the instrument you can see on the top left. And how does it work? You've got actually a schematic diagram on the top right. You just take an X-ray, if you wish, of your sample, like you would take an X-ray of your chest when you go to the doctor sometimes. And instead of taking just one, you are taking hundreds of them while rotating your sample on itself. And using algorithm and big computer, you can actually reconstruct the internal structure of your sample. And this is used in many different fields. So if you look at the bottom left, for example, you see a carbon fiber reinforced polymer composite, and you can see the scale, so 100 micron scale. So the black bar on the image on the left is more or less the thickness of one of your hair, for example. In the middle, you see a piece of concrete with the different components of the concrete, and on the bottom right, you see some pictures of my sample, the one that we collected at Medicine Lake. And I'll show you in the next video this sample that is labeled number 3 and it's circled in red. And this is actually the whole sample seen 3D. And with this instrument, you can actually zoom in the sample and you can see the whole texture of the sample. So what you see here, and the video will pause for a second, you see in white, what appears in white is the solid part of the sample. So it's the glass, volcanic glass. So it's more or less like a glass you would drink in, except it has a little bit different composition. And the dark part is void. And so what we've done, we've passed many of these samples in this instrument, and we've discovered something new. So on the next video, you will see 2 samples from the same eruption, one on the left and one on the right. The one on the left is a normal pumice, something we all expected in our field to see. So you see big void inside, and you see like tiny void also. On the right is also another pumice, but you can tell, even if you've not taken any volcanology class, that it is very different. It seems to be made of different domains with different textures. You see also big crystal, that's the white thing that is disappearing now. And you see that the boundary between these grains or these domains is actually bright, so it means it's more dense. And so that tells us many things about the eruption itself, new things about the eruption itself. It tells you that instead of the magma breaking in tiny pieces and those tiny pieces living their own life afterwards, some of them may collide and may agglomerate and partly sinter, making a whole new sample with zillion of these tiny pumices. So what we have done, for example, and it's a work in progress, we have dismantled one of these samples. So you can see on the left here the 3D rendering of the sample and with some slices, and we've separated the different textural domains. And we were able to make a size distribution of these tiny particles. And as I told you before, the size distribution of the particle can tell you a lot of information about the fragmentation processes. So the single process that will differentiate an explosive eruption from an effusive one. So the process you really want to understand, and that happened in the conduit, and of course that you have absolutely no way to witness with any kind of instrument right now, at least. So these are some of the analyses we do with the samples that we collect on the field. So if you're really interested in volcanoes or earthquake and the Pacific Northwest, I could encourage you to consider registering for my class, Volcanoes and Earthquake, in the fall. So it's a 300 level class, but it's actually open to everybody from freshmen to seniors and all disciplines. Sometimes I've got freshmen in philosophy together with senior in geology. So this class is definitely adapted to everybody. And we'll talk about things like I just said. How do we form magma? How is it transported through the crust? Why do we have earthquake in some places and why not in other places? We'll talk about a lot of things, and we'll take a lot of examples from the Pacific Northwest, from the nice Skinner Butte here in Eugene, Oregon, maybe a mile from this very room, and it's actually directly related to a volcano, or to the ghost forest that you can see on the coast of Oregon and Washington that are related to the last big earthquake in the region that was about 300 years ago. If you want to learn more about the societal and cultural aspect of volcanoes and earthquake, well, as freshmen, you can also take the first year interest group, which is pairing this class of volcanoes and earthquake with an anthropology class called Origin of Storytellings, and we'll look beyond just the science of learning about volcanoes, what we can learn from the traces they leave buried in memory. So from books or letters that were written hundreds of years ago. And so if you're interested in geology in general, volcanology is only a part of what we do here in the Earth Sciences department at the University of Oregon. You can see that volcanology is part of this rectangle on the left, but we study also environmental, geosciences, paleontology, geophysics, and so on. And so this flyer is available on our website of the Earth Sciences with a list of what kind of question we tackle, what kind of job you could get with a career, with a diploma, in geology. So in any case, whether you're interested in volcanoes, earthquake, or not at all, you must be interested in something. You don't know it yet, but you will discover it hopefully in the next few years. And I would encourage you to just stay and be curious. Do not hesitate to ask us, your professors, about their research, their lab, their classes, their interest. Right now, we are able to answer you by email or by Zoom. It might take a little bit more time as usual, compared to as usual because of the condition, but we are here to help you find your way. And so with that, I'll thank you, and I will give it back to Cora now.
Thank you so much. We have some time for questions and have a few in the hopper here. And actually, our first question comes from Julia, and it sounds like she wants some advice from you about something that's sort of semi-related. Julia says, I am learning French and I'm very interested in environmental studies in an international sense. Would you say there are good opportunities in France to study sustainable practices, and which natural areas in France would you recommend visiting?
So, yes, I mean, environment is something worldwide. It's not just in the US, but as I tend to learn with my colleagues working in environment is that environment is really related to policies, and these policies might change a lot. Here in the US, you've got like the city level, the county level, the state level, the federal level. In France, it's different. You've got the France level, like the country of France, but then you've got the European level, and everything is changing. So if you're interested in like the science of environment, that's one thing. Yes, there are definitely opportunities in France. Since it's not my discipline and I left France almost 9 years ago, I wouldn't be the best person to direct you to a particular university. But then if you want to visit France, there are so many places. Such a nice country. We've got the mountain, we've got the forest, we've got the countryside, we've got big cities. You of course know we've got a lot of history and culture that I really miss, because this year I was not able to go back to France. I usually do and see the families, and so it's really sad for me this year. But yes, we really enjoy going back to France every year, and so please email me with more questions about France if you want, and I'd be pleased to take time if I find it to answer your question.
Thank you for that. So we have some more related to volcanology here. One of the questions that we have is, do the eruption deposits you've studied, like say in Medicine Lake, offer any predictability to the size and scope of future eruptions of stratovolcanoes in the Pacific Northwest that would help communities prepare?
Absolutely. Imagine you're a volcanologist anywhere in the world, and you're in charge of studying this volcano that hasn't been erupted in like at least that anyone can remember, at least 200 or 300 years ago. What do you do? How do you know how often it erupts? How do you know whether it erupts explosively or effusively? Well, you look at past eruption. So you dig into the deposits, and so there's a whole part that I didn't talk about, which is dating a product of an eruption. So I know I'm not the first one to study that particular eruption, so I know it's about 1,000 years old. But if I was the first one to study it, I would have need to date it. And so if you do that very carefully for one volcano, you can go back in time and you can start to build a frequency, meaning you know that this volcano is erupting almost every 100 years with small eruption, but once in a millennium, it's erupting a very, very big eruption that can cover the whole region and impact. So now it could impact not only people on the ground, but think about also aviation, for example. 2010, Giachetti in Iceland just shut down the whole European aviation for more than a week. I was stuck in that, so I can tell you about that. And it was a very modest eruption in terms of, it didn't kill anybody as far as I know. And yet, like billions and billions of impact. So yes, studying eruption, how they occurred, and also how frequently and where, and what type of deposit they make. And you've seen some images that I've shown you, but some eruptions just make lava flows, and they are nice. You can actually, I played with magma in the lava flow, and I was not crazy. Many people do that, even people who are not scientists. It's not that dangerous if you know what to expect. And there are, of course, some volcanoes and some eruptions you don't want to stay close by. So yes, studying eruption, like studying earthquake, will help you understand the frequency and the size of these events. And it won't tell you that Mount St. Helens will erupt June 12, 2025, for example. It won't tell you that, but it will tell you that Mount St. Helens is the one volcano in the Cascade right now that is erupting the more frequently. And if you ask any of the USGS scientists in charge of volcanoes in the Cascade, most of them would tell you that they would bet the next one to erupt is again Mount St. Helens. Maybe an effusive eruption like from 2004 to 2008, or maybe an explosive one like 1980.
Will its past eruptions tell us how big the next one will be, like how much damage it will do to the surrounding area? Or
Not directly.
Yeah, okay.
Not directly, but an eruption that is explosive, the eruption I'm studying, for example, Newberry last eruption, that was also about 1,000 years ago, sent ash down to Idaho. The last eruption of Yellowstone, it was almost everywhere in the continental US. So it's like different magnitude of eruption. And you don't know that if you don't study the deposit, and also whether it formed a caldera, for example, Crater Lake. Crater Lake was 50 times larger than Mount St. Helens 98T, for example, and was like at least 50 times less large than the last eruption of Yellowstone.
That's amazing. One of the things that I was reading just the other day was actually a news story about some work that one of your colleagues has done, a PhD student here in Earth Sciences has done around studying the Cascade Network. What do you know about that research that Dan O'Hara has published recently, and what does that tell us? Does it inform the work that you're doing?
So Dan has been looking, as far as I know, and I still need to read this paper that just came out and that he published. He looked at the morphologies of volcanoes, and not only the big one that most of you know and that were plotted on my map a few minutes ago, but also all these tiny satellite vents. For example, if you look at Newberry volcano, it's actually the second largest volcano in the Cascades, and nobody would know because it's very flat and shield-shaped, but it has at least 400 vents, 400 tiny volcanoes that are on top of this big volcano, and each of these volcanoes produced an eruption. Most of them were very tiny with a small lava flow, but some of them were probably larger. So he studied all of these volcanoes, their shape, and of course, because he went back in time much further than I went, I'm usually studying very recent eruption. It might sound weird for you when I said my eruption is like 1,000 years old, but it's still quite young. The deposit is still quite fresh. He was studying eruptions that were like millions years old. And so, of course, in millions of years, you have not only geological events, but also you've got a lot of erosion. So he had to go back in time and correct for that. And he was trying to, as I remember, predict some kind of pattern in terms of frequency of eruption, but on a much longer time scale. So with less resolution, if you wish, like less precision and accuracy, because he just cannot do that, because he's left with whatever is available on the field, of course, but he went much further back. So that's one of the very cool things of our cluster, is that he can talk to me, I can talk to him, we understand each other. We can be complementary, and yet we do things that are very different. And that is something that you may discover when you come to the U or you go to college, is that it's really rare in the US, at least, to have a group of scientists studying the same topic, the same object, whether it's volcano or anything else, without overlapping too much. So we don't do exactly the same thing, but yet being able to talk to one another and tackle very big questions or very big grants, if you wish, together.
Thank you for that. Okay, so this is the last question. You talked a little bit about the classes that students can take from you. There's another question in here. Are UO students able to study how communities prepare for and recover from volcanic eruptions and other natural disasters?
Yes. So one thing we do in that class, and we were supposed to do that, for example, in the spring before we were, with what happened, we couldn't go. We go to Cascade Volcano Observatory. So Cascade Volcano Observatory is in Vancouver, Washington, so right next to Portland. And it is where the USGS folks are actually monitoring our volcanoes. So you go, for example, in a room that is full of monitors with seismometers from all the different volcanoes. And they are the people who will issue a warning, for example, for aviation and so on. And they work together with many different organizations and institutions across the US. For example, whenever you want to monitor a volcano, you need to put instrument. Where do you put this instrument? Is it like a Bureau of Land Management? Is it a national forest site? Is it private land? So you need to discuss with different actors. If there's a disaster, then it's FEMA who is taking the lead. But FEMA doesn't take the lead until there is a disaster. And so it's always working with all these groups. And so even though we worked a little bit on on these topics here in the cluster at the University of Oregon. Our colleagues at CVU are more knowledgeable about all these questions, and so that's why more and more we try to, not only us, but also our students and undergraduate students through classes, have connection with these folks at Cascade Volcano Observatory, or for earthquakes, for example.
Thank you so much. That is all the time that we have for questions.
Thank you.
Again, for you students, please log on to community.uoregon.edu to complete your reflection of this program. It's also worth noting that we're at a critical point in the summer where you will begin to get more and more information from various departments on campus. It's really important that you continue to check your @UOregon email account and read those emails with attention. All of the emails that we're sending you in the coming days and weeks will have a call to action for you, and taking action on these will be critical for your readiness for the fall. For questions about this or any other introduction program, you can go to our website, orientation.uoregon.edu. You can email us your questions at orientation@uoregon.edu, or you can text those questions to us at 541-346-1159. Thanks to you students who are watching us live today. Thank you for your time. And to you, Dr. Giachetti, thank you so much for helping our new ducks get ready for fall.
You're welcome.